Okay, this part of section 3.5 deals with logarithmic differentiation. Sometimes we're not going to be looking at just equations that are written in implicit form, but simply some what are starting out as functions that don't have logs in them. They're not implicit, but there's just so much to be done if you follow the regular rules for differentiation that introducing logs comes in handy to make the work a little bit shorter. So here's an example. We have this function here, y equals the quantity x minus 2 squared all over the square root of x squared plus 1. So think about what would need to be done to find this derivative. First you would need, pause the video if you want to think of it yourself, a quotient rule. Within the quotient rule, when you were getting the derivative of the first, you would either need to FOIL this first, or you would need to use the general power rule or chain rule, and then derivative of the first times the second minus derivative of the second. You would need a chain rule here as well, general power rule, times the first, all over the second squared. And up at the top then you would end up with a complex fraction, because this would be in the quantity to the negative 1/2 would be in the numerator. And if you do, if you would like to, go ahead and try this, just differentiating normally. But what I'm going to show you right now is a way to introduce logs to have it be a little easier. So what I'm going to do first is I'm going to natural log both sides of this equation. So the natural log of y equals the natural log of this expression. Now, why did I do that? How does that help? How it helps is with natural logs I can use properties to split this up. Again, if you want to try to split it up yourself first, pause the video. I'm going to go ahead and just start splitting. So on the left I still have the natural log of y. On the right, I'm going to do a few steps in one. I'm going to change this to the natural log of the top minus the natural log of the bottom. Now when I do the natural log of x minus 2 quantity squared, I'm at the same time going to use the property where I could take the 2 as an exponent and pop it up front as a coefficient. So I'm going to end up with 2 times the natural log of x minus 2 minus 1/2, again taking the exponent outside, times the natural log of x squared plus 1. And if you need to, pause to try to understand how I split it up. Okay, next line. Now that I've rewritten the original function, now I can try to find its derivative using implicit differentiation, because now instead of just a y, this is a natural log of y. That's why I need implicit. So the derivative of the natural log of y is 1 over y. Look at your rules if you didn't know that. And then because it's a derivative of a y with respect to x, we need that extra term. Here and here, I'm going to use that the derivative of the natural log of u is u prime over u. I'm also just going to multiply by the constant. So, it's your coefficient, 2 times 1, that's my u prime, over u, minus 1/2 times u prime over u, now I'm going to simplify this a little bit and cancel this 2 with this 2, and that's really about all I could do. So I'm going to rewrite this all on the next page. Okay, so now the dy dx is almost isolated. All we have to do is multiply, I'll do this in a different color, multiply both sides through by y, and then we have our dy dx by itself. Now, one other thing to note is that this quantity is okay without having a common denominator. I think I am going to get a common denominator, which means I'm going to multiply this times this quantity and this times this quantity and leave the denominator the product of those two things. So 2x squared plus 2 minus x squared plus 2x. Again, that was distributing the minus x through this quantity, minus x squared Minus times a minus gives you a plus 2x. That's all over x minus 2, x squared plus 1, and that's all times y. And the only reason I did that was so that I could combine a couple of like terms, which here is this one and this one. So x squared plus 2x plus 2 over x minus 2, x squared plus 1. And then that's all times y, which normally you actually will see replaced with whatever y was. Y was, if I can remember, x minus 2 quantity squared all over the square root of x squared plus 1. This is about as much as you would be expected to do or as you would see for an answer for that. Okay, there's one more type of problem where we're going to have to use logarithmic differentiation. And it's in a problem like this where you have formulas for a number to a variable base, or you have a formula for a variable to a number base. But look, we have a variable here and a variable here. So there actually is no rule for that. No derivative rule will help you there. So first thing I want to do is squeeze in a natural log here and a natural log here. So now in my next step I have the natural log of y equals, and the reason I applied that, or I took the log of both sides, is so that I could apply the property that takes the exponent out here as a coefficient. Let me make that look better. 1 over x times the natural log of x. So now I don't have a variable to a variable anymore. Now I have a variable times, or a function of x times a function of x. So now I can differentiate both sides with respect to x, and then I would get 1 over y dy dx. On this side I need to use the product rule. So if you think of this as x to the negative first, its derivative is negative 1 x to the negative second. So derivative of the first times the second plus derivative of the second times the first. So maybe I'll do two things in one here. I'm going to just simplify this and multiply everything through by y. So in my last step I have dy dx equals negative 1 over x squared ln x plus 1 over x squared, and that's all times y, and y was x to the 1 over x. Maybe I could simplify this a little bit more. So I could factor out a negative, or I think I'm going to factor out just a positive, 1 over x squared. So if I factor out a 1 over x squared, I'm left with, I think I'm going to put this term first. So that's just going to leave me with a 1, and then this is going to leave me with a minus natural log of x. And then again, it's all times x to the 1 over x. Now, this is good enough for me. So I'm going to do this. But on the next page, I am going to show you how a lot of times you'll see with the Larson book and possibly in WebAssign one more thing done with this. Okay, in rewriting it, I didn't rewrite the brackets, but it was just a product, so it's okay to not have to rewrite the brackets. Okay, right now you have an x to a power down here, and you also have an x to a power up here. Now remember, what you're used to doing is, say if you had an x to the 5th, or I'll just say a, over a squared, that would be a cubed, right? All you do is subtract the exponents. You can think of canceling or subtracting. So one other thing sometimes you'll see done with something like this is to just subtract those exponents of that common base. So now I'm going to have an x to the 1 over x minus 2 times 1 minus the natural log of x. So they're both acceptable answers.